All right, so this is kind of our last meeting before next week's final, which once again will be available all day, Monday through the end of the day on Wednesday. You'll have 2 hours to take it. So once you start, basically you have to submit it within 2 hours. So if you want the full time, you have to at least start it sometime before 10 o'clock on Wednesday, right? Because it closes at midnight. So 15 multiple choice, 2 short answers with about 5 parts to kind of 5 individual questions, each one of those short answers, but all related to each other. Similar to the last 2 exams, show as much work as possible so I can give as much partial credit there on those short answer questions. You've got the 2 practice exams. I should have the 4th Excel assignments graded this afternoon. Once I have all those graded, I'll post the answer key to that. So that would be a good thing to take a look at. Also, once that 5th Excel assignment due date is passed tomorrow, I will this weekend post the answer key. Saturday, I'll post the answer key to that as well. So you'll be able to kind of have that as a resource. So with that being said, are there any kind of questions for me before I kind of jump into things here? I'll wait in the chat. Okay, so there's a couple of things that I want to point out before we get to materials. So on the YouTube page, I put up some additional linear regression examples that I worked through with my other sections. It's the same kind of stuff that we did last class, but just with 2 different data sets. So that's up there on the YouTube page. I'll also be posting, we'll get through all of practice exam B today. I might do parts of A, but I'll probably post an additional video, which is me working through practice exam A and other sections with, kind of identifying which questions I was working on, broken down into a couple little smaller videos so you can really, if you have a specific question as you're looking at those practice exams, find it a little bit easier. So I'll be getting some of those videos up as I clean them up today as well. And then one more thing, sorry, 2 more things actually. So under the practice materials, I've updated this formula sheet to include, and we'll kind of go over this as we go through practice exam B today, kind of how you would find the test statistic for a coefficient. We'll review this today, and then kind of I'll explain why this equation is up there as well. And one final thing, if we go to files, there's this figure out your grade tool sitting there. So if you open that up, it's going to look something like this. So I now have on Canvas, you can kind of see your old online quizzes and Learn Smarts, but because there's no more of those, I kind of put up your grade, your online quizzes with the 3 lowest drop, which is what I said in the syllabus, the Learn Smart with the lowest Learn Smart dropped. And so these are kind of going to be your grades in those categories. As I get the 5th Excel and Connect graded, I'll kind of do a similar thing for the Excel and Connect assignments, dropping your lowest of each type, and then kind of putting those up so you can see what your grade in those categories would be. Now, you only have kind of your current 2 exam scores, but what you can do is figure out your grade tool. So let's say, my current grade grade in the Excel category is an 80. My online quiz grade with the lowest dropped was a 90. Connect grade is a 90. Learn Smart with the lowest dropped, we'll say is 100. And then it doesn't really matter if you kind of flip-flop exam 1 and 2. So I'm having some issue on Canvas where your exam 1 isn't showing up. It's just the lowest and the highest. So I can see it, but for that on the student view, you're not able to see it. So just put in your 2 exam scores here. It doesn't really matter if you got a 50 on the first or the second. But let's say I got a 50 and a 70 on those first 2 exams. I can then play around with, okay, what do I need on the final to make sure I get a C in this class, right? So if I get a 55, I've still clearly got a C. I could probably get as low as a 40. I would still get a C if I was this individual. I could really tank this thing, get a 30 and still, right? You can play around with that final exam score. And this Excel file updates it so that it weights, what your lowest, highest, and second lowest or second highest was, and kind of tell you what your kind of should give you a pretty good estimate of what your final grade would be. Okay, so this will be kind of helpful going into the final, knowing, I know you've got multiple classes. How much do you study for this? Depends on kind of how close you are to the cutoff, so you can kind of see what final exam grade you would need to get whatever your desired grade is. So that's up on Canvas as well. All right, that should get through kind of the housekeeping stuff as we're getting kind of, wrapping things up this semester. Once again, I'll give one more time. Is there any questions not related to like specific problems on the practice exams that anybody has before we jump into that? Wait here. Okay. So last class, oh, here we go. Are you dropping? Yeah, so I will, but obviously the due date hasn't passed for the 5th one yet, so that isn't showing up on Canvas. But I do drop the lowest of each type. So your lowest Connect grade, your lowest Learn Smart, which I already did, and then your lowest Excel. Okay. All right, so, oh, this is the answer key, which is not what I want. I believe we worked through 1, 2, 3, and then we skipped down to 7 and 8 last class. So we'll pick up and we'll work through number 4, okay? So we've got what, 500 men, 500 women, and we've got 37% of men own guns, 31% of women own guns if we find from these surveys. So we've got our sample proportions. I've identified here for you that we'll kind of use men as group 1, women as group 2, and I'm thinking about the difference between men and women, right? Group 1 minus group 2. So I want to build a 90% confidence interval here. So my alpha, the 90% confidence interval would be just 0.1, the area outside the interval in decimal form, right? So 10% in decimal form is 0.1. So I've got my alpha, I've got my 2 sample proportions. I kind of made this one easy, kept the 2 sample sizes the same. We go to, looks like I accidentally closed that for some reason. So we go to our formula sheet. Here we've got some confidence interval equations, and I'm dealing with proportions, right? So I'll plug in my sample proportions, plug in my sample sizes. The only thing I really need to look up is this z-score, right? So it's going to be the z-value that gives me alpha over 2 on each side of my interval, okay? So if I'm thinking about, and I'll get the dot cam going here. If I'm thinking about what I'm trying to do, so I'm looking at proportions. So that formula sheet reminded me, oh yeah, that's the standard normal or the z-table. And I want the z-values such that it gives me kind of alpha total in the tails or alpha over 2, right, in each tail. Okay. So my alpha was 0.1, so 0.1 over 2 is 0.05, okay? So there's 2 ways you could do this, right? You could go to that standard normal table. The area I want in the tail is 0.05, so I look up in the middle here the area I want, so I find what's closest. Looks like at these 2 values. Oh, it's never gonna remember that. All right, there we go. So I go to that standard normal table. I hunt down. I'm in between these 2 values, negative 1.64 and negative 1.65. So I'll use the higher of the 2. We also said that, you know, the negative and positive sign are already built into our confidence interval. So I just need that 1.65 value there. I could have also went to my student T table. I know the area I want in the tail is 0.05. And just go all the way down to this last row, which if we had degrees of freedom of infinity, that would be our standard normal distribution. So I can go down to that last row and get a little bit more exact. So instead of 1.65, 1.645, and then plug that value in. Right? So if you use it out to the 3rd decimal, your result might be a little bit different, but I'll never give kind of 2 answers where if you used it out to the 2nd or 3rd decimal, you'd get something that was so close that you'd go with the wrong answer here. And really at this point, it's just a matter of plugging our values in. So if I had that formula sheet pulled up, and I'll blow this up here in a second, I'll try to write big. The first thing we're looking at is the statistic we're interested in is kind of this sample difference, right? We're then going to add and subtract to that our z-value times square root of first proportion times 1 minus that. And I'm just writing out the formula that I kind of pointed out in that formula sheet. Now it's just a matter of plugging our values in. Right? So 0.37 minus 0.31. We had that z-value of 1.645. And I'm not even going to kind of write that, I'll run out of room, but you can imagine I'm doing 0.37 times 1 minus, I'm just plugging in the rest of my values there. Okay? Really at this point, it's just a matter of getting this entered into our calculator correctly. One thing that can be helpful is remember this guy right here, represents the standard deviation for the difference in my sample proportions. Maybe finding this ahead of time and then plugging in instead of trying to do this all at one time on your calculator might make it a little bit easier so you don't make as many mistakes. I'm gonna blow this up here for a second. So that might be one way to make this a little bit easier for you, is calculate that first. Another thing I want to point out is, if we think about the sample difference we found, it was 0.06. So we're building our confidence interval around this value, so it should be exactly in the middle of our confidence interval. So if I go back and I look at these, you know, if there was an option that didn't include 0.06, which it looks like all of these do, and it looks like 0.06 is kind of smack dab in the middle of all of them. But let's say, for instance, let's say instead we had this one, instead of negative, let's say it was 0.083 or something. Well, 0.06 wouldn't be in that confidence interval, so we could rule it out, right? In this particular problem, there's none that we can rule out based off of that information, but on the exam, there's likely going to be answers that would. I have the exam written, so you know, telling you this with a pretty high level of confidence. So if we do this, let's I'll kind of work through this one real quick so I can kind of tell you what it would be. So 0.37 times 0.63 divided by 500 plus 0.31 times 0.69 divided by 500, 0.010. Okay, so if we round it, I think it's this guy right here. Let's double check my calculation here real quick. But yeah, you should get that kind of 0.109. Okay. So if we get that entered into our calculator correctly, we should get the upper and lower bound there of 0.011 and 0.109. Okay. Any questions on that one before we keep moving? Okay with that? Okay. So what if I wanted to find the test statistic for a hypothesis test here? Now, it doesn't matter what type of tail test I have. I always find the test statistic the same way. So we go to our formula sheet. The test statistics are really just a matter of kind of getting our values plugged in correctly, right? So I'm looking for the difference in two sample proportions. So here's my test statistic equation. I have my two sample sizes. I have my two sample proportions. I can find this P bar first, which is just using my sample sizes and sample proportions. It's really just a matter of kind of making sure that I'm comfortable using my calculator, right, when we're calculating this test statistic. Now, one thing that I want to point out is, if I can get over here, when I'm looking at that test statistic equation, because I've kind of simplified these for us, technically there should be we should be subtracting the assumed true difference here. And then we had what? The square root of P bar times 1 minus P bar times 1 over N1 plus 1 over N2. Oop. Well, I told you from the exam, we're always going to use that assumed true difference of 0. I think even the problem had stated, right, that we were thinking about that difference being equal to 0. I think it was a two-tailed test. So we're using 0 here, so we can kind of ignore this, right? That's why if we look at the actual formula on the formula sheet, it doesn't have an assumed true difference because I'm always going to use 0 on the exam. Right? In every single test statistical equation, our denominator is going to represent a standard deviation for the statistic we're interested in. Well, now we're interested in the difference in proportions, so it's the standard deviation of the difference in proportions. Well, standard deviations and variances are all positive. So if we think about the denominator in all these test statistic equations, they all represent a standard deviation, so they'll all be positive. Okay? So if we know that this denominator is positive, the sign of the difference we find will be the sign of our test statistic. Right? If this is negative, negative over a positive is negative. If our difference is positive, positive over a positive is positive. So when we plugged our values in, 0.37 and 0.31 here, right, that's a positive difference, right, 0.06. So when we're thinking about our test statistic, it should be positive as well, so we could rule out the negative values. Okay? So now we've got this down to kind of 3 different options. if I'm just looking at this, 0.029 seems extremely low for a test statistic. Remember, our test statistics still represent Z and T values. So there's a number of standard deviations away from that assumed true difference the sample difference we found was. Well, our sample difference was 0.06. That's, not, if we're thinking about proportions, the largest difference we could ever find is that 1 is 0 and 1 is 1. So the largest difference we can find is 1. So 0.06 isn't that small. So I'm guessing that's going to be a little bit more than 0.03 standard deviations away from that assumed true difference. So if I was to guess, I'm probably going to guess either C or D here. If I plug everything in, I'm probably pretty sure we get 2.002. So we have what? What were our two? 0.37, 0.31. So P bar is 0.34. So 0.34 times 1 minus 0.34 times 1 over 500 plus 1 over 500, square root of that, and then 0.06 divided by that. So yeah, sure enough, if we do this, enter those values into our test statistics equation, we should get 2.002, okay? But like I said, this one is theoretically possible, but seems pretty unlikely, right? I found a difference of 0.06. That seems like it's going to be more than 0.03 standard deviations away from the assumed true value. Okay. Any questions on this? These test statistic ones really shouldn't be too bad. It's mostly about once you've correctly identified which one you're supposed to use. And look, the problem told you that P hat 1 is equal to this and P hat 2 is equal to that. If you see P hats, right, sample proportions in the problem, and you're looking at these test statistics, I mean, to me, it should be obvious that this is the one you should use, right? If I'm telling you you have a proportion, not only telling you, I'm indicating with the, P hat, how am I going to use those sample mean formulas with sample proportions, right? So I don't think that we should be too bad. Once you identify the correct test statistic, it's just a matter of getting our values plugged in correctly. Okay? So from there, if you had gotten that wrong and I start to ask you about critical values or rejection decisions, it's going to be really hard to get those right. So instead, I'll give you an assumed true test statistic. So let's say, assume that you found the test statistic was 1.45. You're testing against the alpha of 0.05. What's the p-value? And I said the outcome of the test here. I didn't include that in the answer, but we'll kind of walk through that together. Excuse me. And we're doing a what type of tailed test? Well, we have a not equal to sign in the alternative hypothesis, so we have a two-tailed test. So I'm going to look up the p-value here. So what I'm going to do, just kind of visually, is I found this sample proportion, and I'm told that the test statistic that I found was 1.45. Okay. The p-value is the probability I saw something that many standard deviations away from the assumed true difference, or we saw this test statistic, or anything more extreme that goes against the null, right? However, for a two-tailed test, something that was 1.45 standard deviations below the mean or further would also go against the null, right? Because now it doesn't matter what direction of, what side of 0 we're on, that evidence would still go against the null because the null is simply that the difference is equal to 0. So kind of the total area in our tails here is our p-value. So each side has half the p-value. So I could look up the area in this tail, right? And then multiply it by 2 to get my total p-value. So I'll look up 1.45 in that standard normal table because we're still dealing with this proportion example. So my z-value, the test statistic I have is 1.45, 1.45, so 0.9265. Okay. Now, I'll show you an easy way to know that you're maybe doing this wrong. Right? So if I have 0.9265, well, remember, that's actually the area to the left. But if I forget that and I use it as the area to the right and I multiply that by 2, what was it, 0.9? I already forgot what it was. 0.9265, okay. 0.9265, I'm gonna get something that's over 1, right? well, my p-value it's a probability. It can't be over 1. I saw a lot of people make this mistake in the 4th Excel assignment, right? As I'm grading your sections and others. If you get something over 1, you know you made an error, right? Well, and that's because the area to the left of 1.45 is 0.9265. So the area to the right would be 1 minus that, right? Or what, 0.0735? Well, then I have to remember, this is only one tail. This is the value I need to multiply by 2. I should get what, 0.1470. Right? So if I would have been correct, forgotten to subtract this from 1 because I'm looking at the area in the right tail, this is where kind of drawing it out sometimes can help. Right? Now, another way you could have done this one is it's a symmetric distribution. So if you look up negative 1.45, you would have found the area of 0.035 and then just multiply that by 2. So notice if I would have instead, so I know it's a symmetric distribution, so I can look up the area to the left of negative 1.45. So here's my 5, so negative 1.45. Sure enough, I find that 0.0735 value. And then really all I would be doing there is multiplying that value by 2, give me the same p-value there. Okay, so a couple different ways of solving that one. I think if you draw these out, I think it's helpful. Also, just remembering, anytime you have a two-tailed test, if you once you multiply it by 2, if it's something over 1, you probably should have subtracted it from 1 before you multiply by 2 because you probably have the area to the left, and what you actually want is the area in that right tail. Don't want to confuse anyone on that one. So are there any questions or anything I said there? Okay. So 0.1447 there. Now, we don't have the rejection decisions here, but once I find that p-value, we only reject if that p-value is less than alpha, right? So if I'm thinking about what levels could I reject here? So let's say maybe I even asked you a different question where I said, assume the p-value is this, right? What levels would you reject the null hypothesis at? Well, for an alpha of 0.1, or kind of the 10% significance, right? We're thinking about 10% significance, or if we think about the confidence level, it's the 90% confidence level. Well, we're not less than 0.1, so we would fail to reject. Right? Now, I could go through the rest of them, but if I can't reject with 90% confidence, how could I reject with 95 or 99? So if I do want to go through the other ones, if I'm not less than 0.01, I'm definitely not going to be less than 0.05, and I'm definitely not going to be less than 0.01. So here, I'd fail to reject at all levels, right, given this p-value. So they're the kind of rule to remember, right? We only reject if the p-value is less than alpha. Any other questions on that one? So I'll also walk through. So this is a standard normal distribution example. So let's say I had asked you, and this isn't on that practice exam, but for those of you watching this on Zoom and you showing up in person, or if you watch these, I'm trying to give you some additional ones that aren't on there because you showed up. It should be helpful for you on the exam, right? So what if I had asked you for the critical values, right? Well, for a two-tailed test, right, I'm going to actually have a pair of critical values. My rejection region would be kind of the area to the left and right of those. And it should be the value that gives me alpha total in the tails, or, right, if I have a two-tailed test, alpha over 2 on each side. Okay. So let's say for the first alpha, 0.1, right? Well, here, I'll actually do this down here. So if I'm thinking about the alphas that I want to look up, it doesn't matter which one I asked you for, you could do all of them. The alpha over 2 values would be 0.05, 0.025, and 0.005. So I could go to my standard normal table, hunt down in the middle for the thing that's closest to 0.05, find the z value, then look up that one. A much easier way, at least in my opinion, is use that student T table, right? Find those values in the tail you want. So 0.05, 0.025, and 0.005, right? Those were the three values we wanted in the tail. Then just go down to that last row. These are the standard normal values. So 1.645, 1.96, and 2.576. I can find them that quickly, right? So I go down to that last row, looking at those three columns, and I find my critical values. And remember, I've got a pair of them. So it's plus and minus 1.645, plus minus 1.960, and plus minus 2.576. I've now got my critical values at all of them. So if I'm thinking about, if I were to plot these, so here's 1.645, here's 1.96, here's 2.576. And I could do the same thing over here for my two-tailed test, draw my rejection regions. Now that assumed true test statistic of 1.45, if I've got these critical values in my rejection regions drawn out here, well, 1.45 would be somewhere over here, right? This is my test statistic. It's not in any of my rejection regions, so I would, right, fail to reject at all. Same kind of decision I made with my p-value, but here's another way I could do it. So if I ask you in like a short answer question to make a rejection decisions, but I don't specify what approach you need to use, you can use whichever ones you're more comfortable with. You can use the critical value approach like I did here, or kind of like the original question had, you could use the p-value approach, okay? So either one, if I leave on that short answer, if I leave that open-ended, I'll grade it kind of, whichever method you use, okay? Excuse me. Any questions on that one before we kind of, I know it's not a problem on there, but it was kind of one that I added in. All right, so I'm gonna go down here now. We're gonna do a little bit of linear regression stuff. And quite often I use examples maybe that are similar to what we did in class. But let's say I've got, I think this one's a little different. So the table below, I've got this regression where the dependent variable is wage, which is measured in dollars per hour, right? So I've got this Y variable, which is wage, and I include these four independent variables. So education measured in years, experience measured in years, age measured in years, and then gender, which is 1 if they're male, and then a 0 if they're female. So we could maybe kind of call this instead of gender, if it makes it a little bit easier, right? This is kind of a variable that represents that the individual is male, if we see a 1 there. So I give you this regression output, right? I'm gonna ask you some questions about it, okay? So first of all, how would we interpret the coefficient on education? So if we look at this education variable, how would we interpret that coefficient? Well, the interpretation is always the same. It's a 1 unit increase in the X variable causes the predicted or Y variable, or is correlated with the Y variable increasing by whatever the coefficient is. And if it's a negative coefficient, it's that Y variable is decreasing. Right? So 1 more unit of education here is 1 more year of education would predict or is correlated with hourly wages, our Y variable, going up by $1.233 per hour, right? Because that's the units of our Y variable. Now, the other thing when we have multiple variables in our regression, we said the interpretation stays the same. It's just we have to add in holding everything else constant. So if you see regression output and there's more than 1 variable on your right-hand side or more than 1 X variable, you should be looking for this term holding everything else constant in your answer for the interpretation. So holding everything else constant, every additional year or 1 more year of education, okay, so these two look good. This one doesn't even have holding everything else constant. This one is talking about average wages. So we know it's gonna be A or C. And then from there, it's just this one used the incorrect, it was using the p-value, or sorry, no, it was using the standard error. No, we need to use the coefficient estimate. So for every additional year, that's correlated with our Y variable going up by $1.233. Okay, so this would be our interpretation of the education variable. And I could ask you to do that for any of these. This one's kind of an easy one because every variable, the unit is just years, 1 additional year. The only other one that's a little bit different is this gender variable, which is one of these indicator or these dummy variables where it's a 1 if they're male, 0 if not. So if someone is, how do we interpret kind of that? Well, 1 unit increase in these indicator, or these dummy variables, is going from the 0 category to the 1. So relative to a female, if we're looking at a male here, the predicted hourly wage would be about $2.29 higher, right? That's how we do, holding everything else constant, right? So the unit increase is going from the group, 0 to 1, comparing the group that is the 1, to the group that would be the 0. Now, before we freak out too much about this discrimination in pay, we have a pretty high p-value here, which we'll kind of go over here in just a second. How would, let me see, yeah, so I didn't add these questions in, so I'm going to add in a few, just like we can work through some additional ones. So what if we wanted to interpret the intercept coefficient? Right? So we go up here, if I'm trying to interpret this intercept, we said sometimes it'll be a little bit weird, but the way we make these interpretations is if every x variable is equal to 0, the intercept is the predicted value of our y variable. So if every other variable is equal to 0, so this would be like saying, and actually, let me move this so that we can see the output. Move it up here. All right. So a person with 0 years of education, 0 years of experience, and this is where it'll get weird sometimes, is age 0, and the 0 category for our gender variable was and is female. The predicted hourly wage would be whatever that coefficient is, which here it's 8.68, right? 5, I guess. Right, so even though this interpretation is weird, we'll never see someone who's 0 years of age working, at least I hope not. 0 years of education, doesn't seem like there's probably a lot of people out there that even fit that. So even though it's not a practical scenario, that's still how we interpret it, right? It's like this starting point, even if it's a point that we don't actually ever see in the data or actually play out, it's like a starting point, and then as these variables kind of move away from 0, right, the predicted y value would change, kind of going up or down, depending on what situation we're looking at. So that's one thing you could also be asked, is to interpret an intercept coefficient. The other thing that I have here is, what's the test statistic, right? That was the kind of final question here. So if we're looking at the age variable and we're trying to find a test statistic, I said I added in this formula on the formula sheet, which is right here, right? So our test statistic for these sample coefficients, right, or these coefficient estimates, all you do, this should be the easiest points in the exam. If I give you some linear regression output, or I'm telling you about a coefficient estimate, all you do to get the test statistic is take that coefficient, divide it by the standard error. So if I'm looking at that output, I could calculate these test statistics by taking the coefficient, dividing it by the standard error. So if I'm looking at this age variable, negative 0.019 divided by 0.08, roughly what, negative 1/4 or negative 0.25, really close, right? If I actually just divide that age by the standard error. And all I did there, I had a text box in the file over this so you couldn't see them. I just moved it to the side. Okay, so you can actually, if you really wanted to, you could recreate this test statistic column for every single variable, simply take that coefficient, divide it by the standard error. Right? So that easy. Right? Okay. Any questions over anything there? The added question I added in, or kind of finding these test statistics? Like I said, this should be really easy points, right? Okay. What are some other questions I could ask you? Maybe like on a short answer question on the exam about linear regression. So let's say I gave you this output, and I said, which of the following, or which of the variables are significant at the 10% level? Right? So when I'm saying, are these variables significant? Another way of saying this is, are they statistically significant? Or is there a significant relationship between that x variable and the y variable? Another kind of what this really means is, what variables can you reject the null at, right? Saying that a variable is significant or statistically significant at the 10% level means I could reject the null at that 10% level or an alpha of 0.1. So all you're going to do to answer a question like this is go through and see, okay, which of these have a p-value less than 0.1? So I go down here and, we could say the intercept, right? So the intercept is significant. Education is significant. Experience is. But age and gender have a p-value that's above 0.1. So we would fail to reject the null or say that they don't have a significant relationship with our y variable. So here would be kind of the intercept, education, and experience do, but the other two don't. And really remember, oh, sorry, I didn't mean to do that. What we're really doing here with this regression results, right? Every single time, for every coefficient, slope coefficient, we're assuming it's equal to 0. That's our null hypothesis, right? Making the alternative, right? We're trying to see if it's anything other than 0. Well, if I can reject this null, I'm saying that I can reject that the relationship is 0 between that x variable and the y variable. Because if the relationship was 0, that means that they're not correlated at all. Well, I'm rejecting that. So anytime I reject the null, I'm really saying that there's a significant relationship between that x variable and the y variable, which is why for the education experience, I can reject this null and say there is a significant relationship. But for age and gender, that p-value is not less than 0.1. I failed to reject this. Well, if I fail to reject this, then the true relationship between age and hourly wage, or the true relationship between gender and hourly wage, could be 0. They could be completely unrelated. So I can't say that they are significant at the 10% level, or that the relationship is significant at the 10% level. Okay? Any questions? So I would expect to be asked a question like this on the exam. Another type of question I could ask you is, what is the predicted wage for someone with 14 years of education, 5 years of experience, I don't know, let's say they're 40, and female. Right? So how can I come up with this prediction? Well, this is where I added this formula in, right? You would basically, to come up with a prediction for your y value, all you'll do is take the intercept, the estimate you have for the intercept, and then add to that the slope coefficient for the first variable times whatever that first variable's x value is for your hypothetical person. Add to that the coefficient on the second variable times the hypothetical value for the second variable. And then do that for every variable in your regression. So if we're looking at what we have, well, first I'll take that intercept. I don't want to forget that. That's something, a common mistake that I see people make a lot. We always add the intercept into our prediction, right? Even if all the variables were 0, we start at that intercept. We'll then take the coefficient on education, right, 1.233, and multiply it by that person's years of education. We'll then take the coefficient on experience, 0.417, multiply it by this person's years of experience, 5. We'll then take the age coefficient, which is negative here, so minus 0.019, times their 4 years old. Now here, for this binary variable, if they're female, we said this was 0. So we'll take that coefficient on that variable, but it gets multiplied by 0. So really, we didn't have to do that, right? So I don't know if we do this. I kind of came up with these off the top of my head, so let me do the math real quick so you can kind of make sure that you can reproduce this. 27.27. Should get about $27 an hour, right? 27.27. Now, one thing to point out here, even if the variables aren't statistically significant, you still incorporate them into your prediction, right? Because this is kind of what we say is like, this is our regression model. So even if these individual variables aren't significant, but we included them in our regression, we still use them when we make predictions. Okay? And that, diving into those issues a little bit more about like model selection is kind of what would be like the next level or the next topics we talk about in statistics, but we're done, right? So But this is how you would make predictions. Okay. The other thing that I might ask you to do on the exam would be ask or answer a question like, what is the predicted increase in wages if someone has, I don't know, we'll say 10 additional years of experience, right? So I can look at that experience variable and I can tell you the impact of one more year, right? One more unit. Oh. I'll answer that in just a second. So we'll finish this one and then I'll kind of talk about that. So if I know the effect of one more year of experience is 0.417, then the effect of 10 more years would just be, right, 10 times the effect of 1 year. So you would get what? A $4.17 increase per hour. So if you know the effect of 1 unit, you can always find the effect of 10, 20, 30 units by simply multiplying that coefficient by however many units you're interested in. Yeah, on the exam, so the question was related to this was that, will I have to actually run this regression myself, right? So on the exam, I don't expect you to use Excel on the exam. So if I'm asking a question like this, I'm going to give you the output, right? Sometimes I think, spoiler, I guess a little exam spoiler. The short answer question will have something like this, where I give you regression output and then have 5 questions below it, right? That are probably look pretty similar to these 5 questions. Some of these I've worked through. Now, for some of the multiple choice, instead of giving you like big regression output like this, I might give you, it's a good example we have of this. I think it's on the other practice exam. So let me pull up the other practice exam here. I might give you something like this. Like I give you the equation and then I tell you, okay, and it probably wouldn't be as long of an equation like that. It might be something more that looks like this, right? Simple linear regression. And then maybe I tell you, beta 0 was found to be 1.3 and beta 1 was found to be 2.6, right? So I'm on a smaller regression on multiple choice. I might just give you the values and then that short answer, it's going to be more like what we just worked through where I give you this Excel output. Yeah, but you won't actually have to run it in Excel. The only other question from this regression output that I could ask you about is if I'm just looking here, and this is more of a kind of a definitional thing, but I want to make sure we're thinking about this correctly. If I asked you what percent of the variation in hourly wages are we explaining with these 4 variables, what stat would you look at? So we talked about a statistic that measured the percent or the proportion of the variation in our Y variable that we are explaining with our X variables. That was what we said was the R squared. Yeah, right? So if we look at the R squared here, that tells us what percent of the Y variable we are explaining. And if I know the percent that I'm explaining, right, in a proportion, I guess, sorry, the Excel output tells you the proportion, but right, if we just move the decimal point 2 places, we can talk about it as a percent. But if the proportion I'm explaining in the Y variable is 0.37, we'll call it, then the proportion that I'm not explaining would just be 1 minus that, right? I'm not explaining, 0.64, the proportion of 0.64 of the variation, or 64% is still left unexplained, right? I'm explaining about 36%, so about 64% is left unexplained, right? Kind of knowing that definition of the R squared, I could ask you a question, that you'll have to, know the definition of R squared. So if I ask you, what percent of the variation are we explaining in the Y variable or of hourly wage? Well, I might give you an answer of 0.6, 0.368. Maybe I just choose one of the coefficients here. You know that you should be looking at this R squared, not the adjusted, not the multiple. For the sake of this class, we're just focusing on that R squared, okay? Any other questions on anything related to this problem? Okay. So I think that's a pretty fair representation of questions that you could be asked about linear regression. We've worked through kind of the rest of these. You can kind of see, between this, between this practice exam and practice exam A, I'll kind of tell you right away one type of question that was left off of both of these, but it is fair game. It's just when I was creating these practice exams, I wanted to make sure, I knew we were going to do them in class and I was going to go over them. I wanted to make sure we went over these examples. So if we look at that formula sheet, we never really worked through an example where we had sample means and we knew population variances, right? But it's really just a combination of the two, right? Because it's a very similar, we have very similar equations, right, for the test statistics and confidence intervals. The only difference is if I know the population variance, it's kind of like dealing with proportions. I'm just using that standard normal distribution. And if I only have sample variances, I'm using that student T, right? So I would say probably going into the exam, it's, maybe a little bit more, I would make sure you know how to do examples of all three. So maybe going back and looking at some of those connect questions, or looking at that fourth Excel where you had to, actually, no, I didn't give you assumed true population proportions. But going to the Excel file we worked through in class, the one where we had given population variances, the steps are all the same, right? Your test statistic equation is a little bit, once you plug the values in, it looks no different. It's just that you use the standard normal instead of the student T distribution. Other questions for me? Otherwise, I got a couple more things I think I'll do, but. So I can't remember if I did this with you guys last class or not. So if you have questions, also feel free to put them in there and I'll stop. But I think this would be helpful going into the exam. So we've got quite a few different types of examples. So one, we're looking for the difference in sample means, right? And we know our population variances. We also could be looking for the difference in sample proportions. Similar to our one population examples, these were two scenarios where I get to use the standard normal or the z-tables. The other kind of examples we had was we were looking for the difference in means, but all we had was sample variances. We're looking at a matched pairs example where we're looking at the average difference, and all we have is a sample variance for that difference variable. And then although we don't really go through all the steps of hypothesis testing, we were using the p-values, we were calculating test statistics for our coefficient estimates where we had a standard error, right? So all of these, we calculated a variance. So the standard error, if you really want to think about it, it kind of is like the variance of that kind of coefficient estimate, or it's kind of hard to think about this here, but there's no real notation for this, but that's kind of what the standard error represents. So for all of these, we're going to be dealing with that student T distribution. Okay? So this would, having this written down ahead of time would kind of help you be able to quickly identify, okay, I've got proportions, standard normal. I know the population variance, standard normal. Oh, I only have sample variances. I'm looking at a matched pairs. I'm looking at, regression output using that student T distribution. So along with this, I know that we don't actually look the p-values up for linear regression, but we could, right? We didn't, I kind of punt on that topic. Getting into the degrees of freedom of regressions starts to introduce a little bit more than I wanted to in this class. But if we could find the degrees of freedom, we knew how to, we could take those test statistics, right? We were calculating the test statistic by doing this. I could look that up, in a student T distribution, find the area to the left or the right, depending on the sign of the test statistic, and multiply it by 2, because I'm always looking at two-tailed tests when it comes to coefficient estimates, right? So if I were to ask you a question about, if you were to look a p-value up for a coefficient, what kind of test would it be and what distribution? Well, it would always be from a student T distribution, and it would always be a two-tailed test. Any other questions for me? I said it might be a little bit shorter of a class because I thought we'd get through this pretty quick. So like I said, I'll be putting a video up. Oh, we did A. I'll be putting a video up of me basically working through all of practice exam B, except for I didn't do kind of 5 and 6, but you guys, we got to do some match pairs on Tuesday. And then I did another, added in some questions that weren't on the practice exam in that video. So it's me working through these linear regressions 7 through 9, but adding in a lot of questions similar to what I did today, right? So it'd be another good source to watch if you wanted to. It's me working through practice exam B, and then you have me working through, I think, correct me if I'm wrong, but I believe between last class and today, we worked through every single question here on this practice exam. And then you'll have the practice exam B video as well. If I was, just some like helpful hints, I kind of gave you that outline to be good. I would make sure that you can work through these practice exams, right? If you're then kind of still thinking about studying, I would then try to take a look, like I said, at those answer keys. So I know it's Excel, and you don't have to use Excel on the exam, but the process is still the same. The way that, the process you're using in Excel is similar to the process that you're going to be using on the exam. So, for instance, on the Excel homework, if you thought it was if you looked at it, it was a two-tailed test and you forgot to multiply it by 2, you can see, oh yeah, I can see in the Excel file, I should be multiplying this by 2. So those answer keys, like I said, after I get done grading this afternoon, I'll post the answer key, that 4th Excel. After tomorrow at midnight, on Saturday morning, I'll post the 5th Excel answer key. Reviewing those would be helpful. I guess if you want to go from there, reviewing some of the Connect problems that we worked through, going through the lectures, looking at some of the problems we worked through there. Once you get that far, you could start doing things like maybe going back and reworking Connect problems or something. I don't know if that would be as useful as if you get that far. Maybe go back and try to take the practice exams without looking at the answer keys or something like that. Okay. All right. I think we made it through the practice exam. I kind of laid this out for you. I gave you some ideas of what the short answers are going to look like. So it really should cover it unless anyone has specific questions, or even if it's a question about a principle or doing something, I can come up with a quick example. Okay. No question. Good. Anyone on Zoom have any questions about, even if it's about the exam or anything like that? Okay. So I'll get those additional videos posted this afternoon. I'll get that 4th Excel answer key up. I will put an announcement up that probably kind of outlines some of what I'm doing on Canvas. I will do one more review session, which honestly, we're going to finish up what I didn't get through on practice exam A on Monday. Although, no, I probably have already worked through that. So we might be doing some of what we did. But I'll put a Zoom link up. It'll be between 12 and 2 on Monday. Basically, if you have any last minute questions, you can kind of log on and ask those questions to me. But yeah, I will put an announcement up about that. So 12 to 2 on Monday, if any last minute questions, I'll be available and I have a Zoom link available for that. Okay. All right, end is near. Good luck as everyone's studying. Feel free to reach out for me if you have any questions as you are studying. Other than that, good luck on finals. And after that, hopefully everybody has a good summer. All right.